Hey everyone, welcome to this explainer. Today, we are tracing the absolute wild journey of coordinate geometry. We're talking everything from millennia-old urban planning all the way to the math you literally use every single day. If you've ever stopped to wonder how your phone's GPS knows exactly where you're standing, or how architects take flat, blank blueprints and turn them into towering skyscrapers, well, you are definitely in the right place. We're going to spend some time explaining the chapter's foundational concepts today, and we'll see exactly how this ingenious system lets us take multidimensional physical space and pin it down onto a flat piece of paper using nothing but numbers.
So here's our roadmap. First, we'll dive into a quick history of grids. Then, we'll see these concepts applied in real life by mapping Rhiannon's new room. After that, we'll unpack the Cartesian coordinate system. And finally, we'll calculate the distance between points. Let's get into it.
All right, Section 1, a history of grids.
You know, it's kind of easy to think of geometry as something that was just invented by modern mathematicians sitting in a dusty classroom. But the reality is so much more vibrant, and it's deeply rooted in our ancient history. The absolutely crucial thing to understand here is that a coordinate system is really just a practical tool. It's a way to turn physical space into manageable numbers. Think of it like the grid lines on a map or a basic piece of graph paper. By setting up this structured framework, we don't have to vaguely point and say, oh, it's over there somewhere. Instead, we can use precise numerical values to define the exact location of absolutely anything in space.
It's actually mind-blowing to see how this human endeavor evolved across totally different cultures before ever reaching our modern textbooks. The very first systematic use of grids was on a massive urban scale in the Sindhu-Saraswati civilization, way back around 3300 BCE. They built city streets with just striking precision, going completely north, south, and east, west, about 10 meters apart. A merchant back then could literally locate a warehouse just by counting units of distance from the city center. Fast forward to around 628 CE, and the mathematician Brahmagupta formalizes the concept of zero and negative numbers, which is a huge deal. And then finally, in 1637 CE, Rene Descartes comes along and formalizes the 2D perpendicular plane, which basically brings geometry and algebra together once and for all.
Okay, this is one of my favorite facts. It is amazing to think that the ancient city of Ujjaini actually served as the zero longitude reference point for early maps and Arabic geography. Just like we need a starting point on any graph, ancient navigators and astronomers really needed a central anchor point for the Earth, and Ujjaini was that point. The Greek mathematician Ptolemy built on this concept, and later on, Arabic scholars translated those works, calling the Ujjaini meridian Arjan. This ancient, deeply human desire to map the globe really laid the complete groundwork for the exact math we study today.
Moving right along, Section 2, mapping Rhiannon's new room. Let's fast forward from ancient empires right into a modern-day home. This story so brilliantly illustrates the practical magic of coordinates. It's about a sister helping her visually impaired brother, Rhiannon, navigate his brand new room using a tactile, physical grid made entirely of pins and wool. So Rhiannon and his family had just moved. Settling into a new environment is a massive challenge when you can't see, but his sister Shalini used what she was learning in her grade 9 math class to create a rectangular floor map. She set up this brilliantly precise scale where 1 centimeter equals 1 foot. By marking key objects like his bed and wardrobe with pins and connecting them with thick wool, Rhiannon could physically feel the exact layout and directions of his new space. It's just incredible.
But here is the real aha moment. What happens when we take the mathematical x and y axes and overlay them directly onto that very same physical space? Well, the bottom left corner of Rhiannon's room suddenly becomes the origin, 0, 0. The floor running along the left wall becomes our vertical y-axis, and the floor along the bottom wall becomes our horizontal x-axis. Almost like magic, every single piece of furniture, the wardrobe, the bed, the door, now has an exact mathematical coordinate. Shalini's woolen pin map was actually a perfect Cartesian plane the whole time. Which brings us perfectly to Section 3, the Cartesian coordinate system. Now that we've grounded the math and physical reality with Rhiannon's room, let's zoom in further on the exact mathematical mechanics. How exactly do we speak this language of coordinates? Let's break down the core anatomy of the Cartesian plane, which is exactly what allows us to locate objects with such pinpoint accuracy. We start with two lines sitting at perfect right angles to each other in 2D space. The horizontal line is the x-axis, and the vertical line is the y-axis. These intersecting axes slice our flat plane into 4 distinct sections. We call these sections quadrants. Every single journey on this map begins right here at the origin. That is the absolute zero of our two-dimensional space. The precise intersection where the x-axis meets the y-axis is denoted by the letter O. Its coordinates are exactly 0, 0. Every measurement, every direction, every single distance we plot on our graph is anchored right back to this one point.
Now, thanks to Brahmagupta's ancient formalization of negative numbers that we talked about earlier, we can clearly contrast spaces like quadrant I and quadrant 3. Distances extending to the right or upwards from the origin are positive, while distances to the left or downwards are negative. So in quadrant I, the top right, both your x and y coordinates are completely positive. But if you jump diagonally across the origin into quadrant 3 down at the bottom left, both coordinates plunge into the negative. Without negative numbers, we'd literally only be able to map a quarter of our universe.
Okay, pause here, because you always need to remember this slightly counterintuitive rule. It trips people up all the time. Your x value actually measures how far you step away from the vertical wall, and y measures your distance from the horizontal line. Let that sink in for a second. If you have a coordinate point x, y, that first number, x, is your perpendicular distance from the vertical y-axis, measured along the horizontal floor, and the second number, y, is your perpendicular distance from the horizontal x-axis, measured straight up or down. All right, final stretch, section 4, calculating distance between points.
Finding distance on a straight horizontal or vertical line is a breeze, right? You just count the units. But what if the points form a diagonal line? Well, by breaking it down into 3 really simple steps, finding the distance between 2 points that aren't parallel to an axis becomes incredibly straightforward. If you want to go diagonally from point A to point D, first figure out the horizontal distance covered along the x-axis. Then, find the vertical distance covered along the y-axis. When you visualize those 2 straight lines, what do you get? You get a right-angled triangle. And that means we can just use the Baudhayana-Pythagoras theorem to easily find the length of our diagonal line.
So, the formal distance formula from the chapter? It's really just the Baudhayana-Pythagoras theorem in a clever disguise. It's elegantly measuring those shifts along the 2 axes. You take your horizontal shift, which is x2 minus x1, and you square it. Then you take your vertical shift, y2 minus 1, and square that. Add those 2 squares together, take the square root, and boom! You have the exact straight line distance between your 2 points, all perfectly calculated using the geometry of triangles.
Now you might be wondering, hold on, what happens to our distance measurements if our points wander into the negative quadrants? If we're suddenly subtracting negative coordinates, does our distance formula break down? Does the distance itself somehow become negative?
Well, it turns out that reflecting a shape across an axis into negative territory brilliantly preserves all the lengths and distances exactly as they were. It makes absolutely no difference if your x or y shifts are negative. Why? Because we're simply measuring the absolute shift along the axes. Plus, when you square a negative number in the Baudhayana-Pythagoras formula, it becomes positive anyway. The math naturally protects the reality of the physical space. I mean, a 5-foot bed is still 5 feet long, even if it's placed in a negatively numbered quadrant of a room. Since coordinate geometry is a millennia-old tool designed specifically to locate our exact place in the universe, what hidden grid in your life will you choose to map next? We've seen how ancient civilizations meticulously planned cities, how Arabic scholars mapped the stars, and how a sister helped her brother navigate his very own bedroom. The Cartesian plane isn't just a bunch of numbers on a page. It's a powerful lens for seeing, measuring, and understanding the entire world around us. So take a look around, your room, your street, or your town today, and try to imagine the invisible grid that connects it all together. Thanks so much for joining me on this explainer, and keep exploring.